Okay, hi everybody. So let's start with the afternoon session. So we're going to start with Dorival, who will tell us about entanglement and Bayer inequalities and with boosted tops. So please go ahead.
Thank you, Al. Thank you very much. So this is basically a working collaboration with KC Kong, Cosmos, and Alberto Navarro. So we are all here probably due to the recent advances in quantum computation and also the Nobel Prize. We are all excited in terms of, from the high energy perspective, what we can do with all these new advances, right? How can we use these new observables at the high energy regime, bringing these measurements that were performed at very low energy to high energies? So in this regard, the LHC really provides us a unique opportunity. It's the highest energy collider that we have that can provide a TV scale. So when you do the comparison between the typical entanglement for photons, we are more than 10 orders of magnitude in energy that we can probe at LHC. So we can really scrutinize at a very precisely what in principle can happen for entanglement, Bell's inequality, you name it, for the quantum correlation. So in this regards, the top quark per production is really an optimal candidate. This was presented to some in the previous talks, but I would like to take the opportunity also to go in more detail here. So as a particle physicist that does a lot of collider phenomenology, when you start thinking about how to analyze the top now in terms of quantum system, we have to analyze in terms of a spin density matrix, right? So it's quantum mechanics 101. So how do you fully describe the spin half particle? You can fully describe by this spin density matrix where you have three polarizations associated to the top. So you can extract the three polarizations this way here. However, when you look at the top is quite a complex object. The top, in particular, has color. So the top can hadronize, and you can have spin correlation effects. However, the top is unique. It's very special. So it decays before it hadronizes and before spin the correlations. If you try to think about, oh, we can play the same sort of game for big quarks, for instance, it doesn't work as well anymore. The big quarks orders of magnitude apart from the top quark, and the hadronization spin flip effects, they start playing a role there. So the top is really unique. But how do we do it? We, of course, do not measure directly the spin of the top, doing Stern Garlic. What we do, we look at the decay products of the top. And when you look at let's say that you have a top decay, and I use the decay product as a spin analyzer for the top. The most sensitive ones are the charged lepton and the down quark that have maximum spin analyzer, so the coefficient sitting here is maximal, and then it's followed by big quark, neutrino, and U. If you want to analyze, therefore, some sort of correlation using hadronic top, we need to find ways to access what's this D quark here in particular. This will come later on. All right, so now, instead of only a spin half, we want to analyze two spins, two top quarks, to analyze correlations between them. So in the most general form, you can write the TC bar system in this way here, where you have here the polarization for the tops, three coefficients for the polarization for the antitop, and the correlation matrix, the CRJ. So you have in total 15 parameters without imposing extra constraints. But due to the LHC, as you have, this is dominantly produced by a QCG. So due to P and CP, you have that the polarizations are zero. And the CRJ is equal to CJI. So simplifies quite a lot. When you go to the Helicity basis, this even simplifies further. So there you have that only the diagonal terms, they are non-zero, and one of the diagonal term is non-zero. You may think, what about higher order corrections? This is at leading order. If I start looking, for instance, a high order QCG or electric, this picture basically does not change. So to very good approximation, we can use this here. And that's what I'm going to use in the forthcoming slides. So this is spin density matrix that had 15 coefficients. Now you are reduced to finding 4 coefficients. Okay? But if you have been long enough around, you may be asking yourself, all this question that we have now for entanglement, this reminds me quite a lot of the questions that we had before about spin correlations for tops. And this goes back to the Tevatron times. So there, at that time, people like these two authors here suggested that we can look and check if the case of the tops are correlated or not. At that time, this seems to be kind of obvious, right? Of course they are correlated, so we should see that. Similarly to what we think about the entanglements. Of course the tops are entangled, or the Bell's inequality should be violated. So the question is very similar to what we have at that time. So people really followed through, and we kept on measuring. We are measuring till this day if the topics are correlated or not. And we have such a good control now that we use this for looking for new physics, right? So what was a theoretical question if you have a correlator or not correlated, now turned out to be a good probe for new physics. So in my view, that's probably what we want to take out of this entanglement or Bell's inequality. At the very end is some sort of probe for new physics, or checking if maybe following the previous talk, if this entanglement can be brought to a fundamental principle, if this really, we really have entanglement as expected in certain theories or not. So, but one thing that's a source of confusion here, when you look for correlated or uncorrelated, that's a very weak condition on the spin-density matrix. You are simply imposing that the Cij is non-zero. But in entanglement or Bell's inequality, that's a very restrictive condition for the spin-density matrix. And they follow this hierarchy of that as presented over here. So let's go to entanglement. For entanglement, the way that we entanglement is basically if you can write the spin-density matrix as a convex sum like this, it's separable. If you cannot write like this, it's entangled, period, right? It doesn't matter if it's a space-like separator or not, but that's the only condition that you have for entanglement. So in this regard, if you do a measurement over here for an entangled state, if you know the spin here, you would know the spin of the other candidates. So what people typically do is try to impose this so-called Peres-Hordek criteria. And if you have at least one non-negative eigenvalue, the system is entangled. So if you implement this for the TC bar system, with those conditions over there, you have two sufficient conditions for entanglement that are shown over here. Everything here is going to be calculated in the Ricci basis. So if what you need to do is basically obtain those coefficients here and see which one of these inequalities is the most relevant for the TC bar system. So when you extract those coefficients, so this is the CKK, CR, CNN, what you see is that over the full phase space of MTC bar cosine theta, CNN is negative throughout all the regime, and you have that the CKK and CR that are in absolute value here, they follow the same sign of pattern. So the inequality that tends to be most relevant for us here, when you do numerically check what's the pattern that you have, is this one over here. So you single out this inequality. All right, so we have an equality now for entanglements. So if the system satisfies this inequality here, it's entangled. What you see is that you have two disconnected regimes where you have entanglements. The threshold, as we saw in the experimental talk, that's where the experimental results, the current experimental result sits. But you also have this boosted regime. So here you have a singlet state, here a triplet state, and they are disconnected from one another. Now, what I want to advocate that while the current analysis focuses on the dileptonic case, what we can do, we can still focus on this regime here. And we have quite a lot of data that we in principle can, even with the current data sets, have sensitivity for entanglement in this regime here. So there are four main reasons to look at a boosted regime in the semi-leptonic case. So in the semi-leptonic case, you have 6 times more data than the dileptonic. The other condition is that you have an easier reconstruction, so you are going to have less of an effect for the reconstruction when you obtain this entanglement measure. The other thing is when you go to the very boost regime, you are going to avoid part of the complication. This has nothing to do with the experimental analysis, right? It's just the theoretical modeling. We don't have a very good theoretical modeling at the threshold regime. We don't know how to do. We don't have we know in principle how to do, but we don't have access to a code that does all these threshold corrections. So if you have an analysis in here, we cannot give you to a very good precision what would be the theoretical estimates. You can of course do the experimental analysis, but the theory estimates we cannot give you. But here we don't have these threshold effects. Okay, so in principle, in terms of a theoretical standpoint, you have a better modeling over there. The other thing is when you go to the very boost regime and you focus on the semi-leptonic top, at the very high boost regime, the tagging efficiency for the hadronic top is higher. And so this well matches with this sort of analysis here, the boost regime. So in particular, you can use the several top taggers. You could use in particular this one here called the HEP top tagger. But I'm just saying that there are many features, many virtues to look at the semi-leptonic top and the boost regime. But there is one thing that is not so trivial, which is we typically use for the why it's nice to look at the leptonic, because you have a polarizer here, and that's the charged lepton, and it has a spin analyzing power of 1. But if you have a hadronic top decay, how do you do that? So the easy choice is that to try to use the B quark. And the B quark has a spin analyzing power of 0.4. Okay, that's the simplest case. At the HLIC, Bs are basically leptons, right? The tagging efficiency is so good that it's almost like a lepton. But you can do better, right? So while it's scrambled, what would be the down quark here? We only know that the top decays to, you have a hard and the soft quark. We do not know which one is the candidate for the down quark. You can do, if you do better than this 0.4, if you go to the top rest frame, it's known for quite a while that if you take the softest of the jets, you have a spin analyzing power that goes to 0.5. But we can do even better. Well, if you define a direction here, which is given by some weighted sum between the soft direction and the hard direction, we can define this weighted sum leveraging on our information of the Helice angle that we know for the down quark decay. So we know that the hard jet tends to be more forward at the top rest frame, and the soft jet tends to be more backward. You can model that in terms of the Helice angle and have some weighted sum for this optimal direction here. If you do so, it can be shown that the spin analyzing power is uplifted from 0.5 to 0.64. So we can use this as an analyzer for the top direction, even the hadronic case. So using that, what you need is to identify what would be these light jets and the B quark. So the B quark is easy, but the light jet is not so easy. So what we do here to do the subjets quark mapping, we do use jet substructure, where you are going to have 3 subjets over here, and one of them will be tagged, the other 2 will be the soft and the hard jets. So when you do that, now you can use what we just discussed to define this proxy for the down quark, which is this optimal direction. So doing that, you can obtain what's the entanglement now, extract this coefficient CKK, CR, and CNN, and obtain what would be the entanglement as a function of the luminosity. That's what we obtain here. And what we see here, similarly to the dileptonic case, you can obtain entanglement even with the current luminosity above 5 sigma. So what about Bell's inequality? So Bell's inequality is a more restrictive condition in the spin density matrix that can be distilled in the form of the CHSH inequality. And in the case of the top, basically you have the top decay here, the top energy top decay, and you define these 2 directions in each side to obtain this, to extract this inequality. So when you perform that, and you see that you end up with two basic inequalities that can tell you if you are satisfying the Bell's inequality. So which we name here as a B1 and B2. And similarly to the case for entanglement, you have there in the entanglements, you would have the threshold regime and the boost regime. Here for the Bell's inequality, only one region is relevant, the boost regime. So this favors that we should be, this channel, in particular the semi-leptonic top, should be one of the key channels for us to look there because of all of those reasons that I advocated before. And we have 6 times more data sets to start analyzing this boost regime over here. So when you look at the projections for B1 and B2 as a function of the luminosity, you see that the HLHC, you have a sensitivity that's about 4 to 5 sigma at the HLHC for B1 or B2, with a slightly better preference for B1. That seems to be a bit more sensitive than B2. So just while for the entanglements, all this discussion of loopholes, they are not there. You only have to show that the Peris-Order criteria. For the Bell's inequality, the thing's a bit more intricate. So in particular, collects here the discussions that we had yesterday about the loopholes for the tops in particular. So in the case of the tops, we have this free will loophole where we basically have to have an external intervention to choose the measurements. So we cannot do that LHC, right? One may argue that you can define the directions. They are defined basically randomly inside of the, for the top of the case, but that's defined within, let's say, a box. We don't have access to that. So we cannot close this loophole. The other one is, what about, are they causally disconnected, these two tops? So you can define on the statistical level at the very boost regime that they may be causally disconnected. But again, this is only at the statistical level. The other thing is the detection loophole. So here we have absolutely no hope. We always, when we do this sort of analysis, we look at the subset of events. So we always bias the analysis, but there is no way around. So should we take this seriously? I don't think that this is a no-go. The LHC was not designed to do any Bell's measurements. We have it as for free, so I believe we should keep on doing. And all these loophole-free setups, they took like decades for people to try to obtain that. So this is absolutely a no-stop for us. We should keep on going. So I believe that we are just at the very beginning. And that's what we saw here with James' talk. And I hope now the future analysis from Atlas and CMS will also start obtaining now what would happen for the semi-leptonic tops. And I'm aware that this is already being pursued in both Atlas and CMS. So as a summary, the LHC provides really a unique opportunity for us to study entanglements, Bell's inequality, or any other quantum correlation that we may have. And in particular, we can access, really do a tomography process where we fully access the spin density matrix for the TC bar system. And what I try to advocate here is that the semi-leptonic tops really provide you an optimal framework to do that, because you have a very high event rate, and you have easier reconstruction. You can do the boost top tagging really well match with the analysis, and you can define a hadronic polarimeter. So even what we obtain is that even with the current data sets, you can obtain entanglements for the semi-leptonic tops. And the Bell's inequality and CHSH may be accessible between 4 to 5 sigma. That's all for me.
Thank you, Dorival. Very nice talk. Questions?
So I had a question on, well, I had a question and a comment. I'll do the comment first, maybe. So your comment you made about the there being threshold effects that we don't really know what to do with yet, compared to the boosted, where we have a reasonably good idea of what to do. I think that's mostly true, but I think it's not true to say that we understand the boosted regime perfectly well. No. This is where we start to see the really higher order effects matter and the electric weak corrections and things.
We don't have a. We have the higher corrections, right? But at the boosted regime, we avoid all these threshold effects.
You definitely avoid the threshold effects, I agree. But there are other considerations, is my only point. But then
you also have the higher effects at the threshold regime as well.
Yeah, that's true. Well, it's debatable how big they are. But okay. My impression, though, was on the uncertainties on the projections versus the luminosity. Mm-hmm. What's going into those projections? What uncertainties are going into these projections?
Yeah, here we try to first of all, it's a phenomenological approach.
Yeah, sure.
It's not I don't have all the uncertainties that you have within the experiments, but we try to include as much of this information for the detector effects there, and but we probably don't have as much information as you do.
Did you try to include any sort of assumptions on things like background subtraction? Because here this is the region where there's not too much background when you go to really boosted, but it's very, very poorly understood in that region.
So what we did is, this analysis, basically, you end up, we require a hadronic top tagging. We require 2 B-jets. And when we do the simulation and check the backgrounds that we have, our backgrounds are below 2%. So we are fine with that.
So, okay, thanks a lot. I'm a bit worried about this optimal hadronic polarimeter that you define, especially when you try to reconstruct. So what kind of systematics did you consider?
You should be, if you are worried about that one, you should be worried already about this one here.
I'm worried about everything.
Yeah, you can be worried even with this one here. So here, this is the softest of the jets in the top rest frame, which is this already has all the uncertainties that you would have over here. Okay, so this one here, this is done since the Tevatron times. People do it. Okay, we also do it at the late stage. So all the uncertainties that you may have here, you are going to have over here. Okay. So this was shown to be possible to be done.
Okay.
So hi, thank you very much for your talk. So my question is also regarding this slide. So if we would be able to do charm tagging within the jets that are within the top jet, would it be better than this? Because then we will know the direction of the light jet.
Perfect. So here, I didn't talk anything about charm tagging. So you could add the charm tagging as an extra layer of information. So while for the fourth generation, I don't have any extra information. The only thing that I have is kinematics. So the best that I can do is this over here. But you have this extra layer for the second generation. So you can do charm tagging to further improve this sort of analysis. Yeah.
Another thought about this is the possibility of adding the tau plus channel to the lepton plus Z channel, having one hadronic tau and then the hadronic top.
Yeah.
Is it possible to preserve the spin information of the for entanglement from the hadronic tau decay coming from the W or not? Or is it loose? Top to W and then the W to tau that decays hadronically.
Yeah, so in principle, yes, but we haven't done that. So we didn't do the analysis for that.
Yeah, it's more challenging. The tau will have a part that you don't see because of the neutrino, right? Experimentally. So.
But in the tau plus Z channel, the only neutrino that you have is from the tau, because the other top is a hadronic. And we can reconstruct perfectly the hadronic tau decay, so we can determine the neutrino.
Okay, I don't see any questions. I have one. Can you go back to where you showed the results for the, and the selection? Okay, for example, this one. No, slide, yeah, exactly this one. So both here for the entanglement and also for Bell inequality, you impose some selections for MTT and for cosinus theta. So, you know, just to get a feeling, because you look at semi-leptonic decay, so the statistics should be better, as you noted correctly. Right. What is roughly the number of events that you expect to have with this cut and with the one for Bell inequality, let's say with run-2 data that we have?
Oh, we have all those numbers in the paper. I forgot, I don't have it up in my head because we have two different regions for entanglement and Bell's inequality. So I don't have it on top of my head, but we have the numbers in the paper.
Order of magnitude?
So you're going to have
hundreds, dozens?
No, you are going to have, for entanglement disorder, thousands. Okay. So you have, and for Bell's inequality, like maybe close to 1,000, maybe.
Okay, so this is something we can definitely work with already.
Yeah.
Okay.
At the high, this is the LHC even with the current luminosity. Yeah, I can. So it's sort of a femtobarn, more than a femtobarn for entanglement for this region here. For Bell's inequality is it's close to femtobarn. We have again the precise number we have quoted in the paper.
Maybe just a follow-up. What is the operator you use for the Bell inequality? Is this one here?
We are using the CHSH inequality, which translates to these two inequalities over here.
But why don't you, I mean, has it been shown that the violation is maximized by this, this other operator, that you take the two highest eigenvalue of C transposed C? Why don't you use that? I mean, because this is not maximized, you know, you can still rotate and maybe you find a larger value. So it would be, the best thing to do is to take the operator that you know is going to be the largest.
Yeah, it can be shown that the
no, this is not
all of these studies, including yours, Yob.
Right.
What can be shown that this translates to this two sorts of inequalities here.
No, I don't think so.
The directions that you choose is similar to what people do to the photons. This A1, A2 here, similar to what you define for the photon analysis, actually.
Yeah, but with that operator, you don't have to worry about the direction because you are guaranteed that it's going to pick the direction where this value is maximum. So I'm just saying that.
Yeah, I guess, but that here you have the advantage that it's easier to measure, right? You just need two parameters and not the full spin density matrix.
Since
yeah.
You have the full C.
Yes. Jay.
I'm saying it's probably you get
a better sensitivity.
Yeah. Okay, this will be the last question, and then we can have to continue.
Really short comment. I'm not sure if it applies that well, but not specifically in the context of Bell inequalities, but there have been studies to see what is the way of maximizing the values of the spin density matrix, for example, which, since you want the trace, I imagine it's very similar to this argument. And this NKR sort of formalism is very close to being maximal. There's a slightly better one you can do where it's called the off-diagonal basis, which you can do. But that only optimizes one of the elements of the trace and at the expense of the other two. So when you're doing something like a Bell inequality like this, I suspect, no one has shown it, but I suspect it doesn't help you very much. I think this is probably as close as you can get to being maximal. I don't know for sure, but it's a guess.
Why you may think that by choosing a more general, you may have a better sensitivity, but the thing is for the top, at the late C, the spin density matrix turns out to be not so complex, actually. As I advocated at the very beginning, because you have this QCD production of the TC bar system. So the polarizations are gone. All the coefficients associated with polarization, they don't play any role. And the CIJ, you basically have three, the diagonal elements and one off diagonal. So you have 4 degrees of freedom in this spin density matrix. So it's quite, you don't have the 15 coefficients, but only 4 coefficients that you have to take care of.
Is it urgent? Okay, let's keep something for the panel, okay? So let's thank Dorival again.